Let's continue our study of common Java idioms by looking at the collections class. Here's the problem statement. Learn to use the collections class to perform useful operations on array lists. Now, the collections class is an interesting class. It's a group of useful methods that can be performed on array list objects. Unfortunately, it also works for different types of objects, and so we're going to have to be a little bit careful. Now, examples of the kind of things that are available in collections are sort, minimum, maximum, fill, shuffle, rotate, index of sublist, reverse order, replace all, swap. There's all kinds of great stuff available. Another warning is that there is a class called collection, and there's a class called collections with an S on it. That collections class is the one we're looking at. Very easy mistake to make when you're programming. Now, there is lots of strange syntax in the collections class. If you continue studying Java, someday this will all make sense to you. But for right now, just ignore it and think through what makes sense, because actually all these classes are very logical if you just think about them the right way using the Java idioms. All the methods in this class are class methods, so that's a little bit like the math class, where all the methods are class methods. Another way of thinking about this is the collections class is a utility class. It doesn't have any data of its own. It's simply putting together a group of useful stuff under one title. Here's some of the rules for reading the API. The T between angle bars, parameter, means any object type. Now the ones we're going to use at this point are string, integer, and double, the same ones we've been using all along. Array lists can be used for any parameter or return value that has either a list with the angle bars or a collection with the angle bars. That just has to do with the fact that array lists have order, which is what lists need, and are general collections. Don't worry about what it means too much. Now you're going to ignore anything that uses another class like set or map or enumeration. We don't know about those classes yet, and an array list does not fit in with those. So we'll just ignore those methods. So let's work on one. Let's create an array list that contains the values from 1 to 10 and print with a single instruction with no loops allowed. Now this relies on one of our Java idioms that we're already familiar with, and that's that the systemoutPrintln method calls toString on any object that it encounters. Now all object classes have a toString, and most of them work pretty well, although not all do. Subtleties like this are things you'll understand in your next Java class more than this one. So here we are in Eclipse. I've set up the code so that we'll have 7 different experiments, and the main program just calls them one after another. We may turn those on and off as we wish. So here's experiment 1. We're going to create our array list of integer objects, and of course construct it. Now in this particular case, we know how to construct it. We know what the size should be. When you know the size, which is not something you always know, you always put it in as a parameter because it makes the class more efficient. So for int I is 0, I less than 10, plus plus I. Whoops. I cheated. I used my favorite loop instead of the loop we currently know. Sorry about that. So what we're going to do is mylist.add count plus 1. Remember plus 1 because count started at 0. And then, of course, increment count. And let's see what happens when we do just printing the list, right like that, in one statement. So what's going to happen is mylist.toString is going to be called, and then it's going to step through the list. So there's a hidden loop inside of this. I want to call your attention to one other thing that I did here. Notice that I'm adding an int instead of an integer. That may seem a little bit weird, but Java does something behind the scenes called autoboxing, where it takes integers and automatically creates int objects. Now, I'm a little bit worried about leaving that in there because I'm not sure that's going to make sense to you. So I'm going to actually, even though this is legal code, I'm going to put a little bit more formal code in there. So we're actually constructing those integer objects. Okay, so let's run experiment 1 and see what happens. So there we go. So you can see what the toString method in the array list does is it uses the square brackets and comma separation to tell you what's in the list. Perfectly fine for what we're doing. Now I'm going to comment out experiment 1 because we'll do another experiment in a few minutes. Here's example 2. Let's write a method that creates an array list containing the numbers from 1 to 100 in random order. This is a little harder than you might think, because if you just randomly pick numbers from 1 to 100, you're going to get repeats of some numbers and other numbers will be missing. So that isn't what we want to do. Instead, we want to use some of the cool things that were available in the collections class. So what we're going to do is start with the elements in sorted order and then shuffle them. So that's one of the neat methods that was available. Let's go to the collections class and take a look at that method. Here we are in the collections class, and we're looking for the shuffle method. They're, of course, in alphabetical order. So notice we know we can use this one because of the parameter. Remember, anything that had a list is okay for an array list. So this randomly permutes the specified list using a default source of randomness. All permutations occur with approximately equal likelihood. Ooh, lots of hard words. What it basically means is it's going to shuffle things around. So really the shuffle name is much more useful than the first method there. And then they use lots of little details. So it says the implementation traverses the list backwards from the last element to the second, repeatedly swapping a random selected element into the current position. So they're giving you details about how this works, which are nice to use. But what we need is really just the name of the method and what the parameters are. So here we go. I put a constant in here, a size of 10 that we didn't use in our first experiment, that probably we should increase to 100 now and use. Let's copy our code for creating the array list. No reason to reinvent the wheel. Only instead of 10, we'll use size. And we will shuffle our code. So remember, we have to give the class name. And then we're certainly going to want to look at it. And we know how to do that easily now. So there we go. Now, in terms of checking whether this worked correctly or not, we've got a problem. The problem is 100 is too big. We can't see all the values on the screen, and it's not easy to check that each value is occurring only once. So while we think we've done the right thing, and while everything's looking promising, we're not sure. This is where that constant really pays off. If we pull it down to 10 instead of 100, we now should be able to go through and check and make sure that our shuffle is working correctly. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whew, there we go. The next one we want to try is linear search. That is, stepping through the elements one at a time and seeing if we can find them. We need to think a little bit about what Java idiom makes search work. So if we're looking for something, what do we have to do? Now you might think equals equals at first glance. But the problem with that is that works with primitive data types. It doesn't work very well with objects because we need to do deep comparisons, not shallow comparisons. Now, this is something that you've probably read about in Chortle, but let's actually review it a little bit. Suppose we have a string S and we create a new string Abby, one of my dog names if you're wondering why you keep hearing about Abby. Then we have a string T, which gets the reference for S, and we have a string Q, which is another new string which contains Abby. Let's take a look at what this looks like in the computer memory. So our string S is over here, and here's the first string that was created. T has the same reference, so it's pointing to the same object that S is. Q has a new object. If we do an equals equals comparison, a shallow equals, then S and T are going to be equal to each other because shallow comparisons only compare the references. They don't actually go down and look at the objects. That's why they're shallow instead of deep. The deep ones, notice, would have to go and follow those arrows another layer down. So if we compare Q and S using a shallow comparison, using equals equals, that means that those will not be equal to each other even though the objects contain the same characters. So this is where shallow comparisons are done. They're done on the references, not on the objects. Now let's consider a deep equals. S and T certainly will also be the same with a deep equals. This is the dot equals method in the string class. The reason is because they're pointing to the same object. So those objects, since they have the same reference, automatically have the same characters. But Q and S are also going to be equals to each other using a deep comparison. And of course, Q and T will be equal to each other's too. So this is where deep comparisons are done. That's why we call them shallow and deep, is shallow occurs up with the references and deep occurs down with the objects. We have an algorithmic oddity, and that's that collections doesn't support linear search directly. Let's go and take a look at that. So we might expect a method called something like maybe contains to be in here. Contains or search are both names that we've seen in other classes, and so we might think that they would use the same names here. When we look, we don't see anything called contains. Remember, they're in alphabetical order. And we don't see anything called search. And we don't see anything called index of, which is another one of the search methods that might be available. So we've got a problem. There's no search, there's no contains, and there's no index of. There is, however, index of sublist. Now, there's a problem with this, and that's that this isn't the signature we were hoping for. This is looking for a sublist target inside of source. So target might have several elements on the list, and it would see if source has a sublist, that is a group of elements in the same order. Not really quite what we wanted. If we take a look above it, we see another possibility. We have a method that's called frequency. Now this returns the number of elements in a specified collection equal to the specified object. Well, that's sort of interesting, because if you think about it, what would happen if the frequency was 0? Well, that would mean the object wasn't in the collection. And if the frequency is bigger than 1, or 1 or bigger, big difference on those two, remember that's a boundary condition, that would mean that the object was there. Interesting. So we really don't have the methods that we want, but we have something we can use. Now, one of the tricks to using classes like collections is to be clever about how to reuse these methods in various interesting ways. Although, by the way, if I had written this class, it would certainly have a contains method. So with frequency and index of sublist, we're going to have to be a little tricky to make it work. And we might want to think about what would be the difference. Well, with frequency, we're going to find out whether the object is there or not, but we're not going to find out where it is. On the other hand, with index of sublist, we're going to find out where it is. So we're getting a little bit more information in index of sublist. Now, when we were looking at the API, we didn't read it very carefully. And so we might want to think of what index of sublist will return if the object isn't found. Well, in most cases, just like in the array list case, what it's going to return is -1. So we have a couple of different possibilities we can work with. So here's example 3. Find out whether the number 5 is in our shuffled array using our sneaky workarounds. So we want to do this first. Now, one thing you might have considered here is that we might have been wise to create a parameter for experiment 2 and to pass that data back either using a return value or using a parameter. And in fact, I agree with that. But remember, right now, we're just playing with code. And so whatever we can do to make it easy is probably a good thing. So let's use frequency first. Okay. Now I'm going to put some comments in here. So, if collections.frequency of my list in value is 0, system out print line, 5 is not in the list. Else, system out print line, 5 is in the list. And of course, we should spell print line correctly. Okay, now we probably want to turn off experiment 2. So we can just run experiment 3 by itself. Five is in the list. So that worked great. But it didn't tell us where 5 is in the list. So that's a shortcoming of this. Let's go and do it the other way. If collections dot index of sublist for my list. Now remember, we've got another list there that we're going to have to find. So if that is -1, then we'll do system out print line. 5 is not in the list. Else, we probably want to check and make sure the index is correct. Now that means we're going to have to rewrite this code a little bit. So let's call it differently. Of course, we've still got that parameter we've got to worry about. And now we can just check to see if index is -1. Okay, so what we needed was a list. So we're going to have to create an array list of integer equals new array list of integer. And in this case, we know we're only going to need one element. Whoops, forgot to give it a name. I'm going to call it target. So we're going to do target.add our value. Now notice that's an integer object, so that's good. And so we're going to look for a one element list target. Okay, let's run the program. Five is in the list at index 5. Well, that's kind of coincidental. Are we sure that we've got our list shuffled? It was shuffled here, and we haven't done anything that should have changed that. Now, that could have been correct, but I think what we want to do to check this a little bit more carefully is to actually print out our list at this point. That way we can check our code better. Five is in the list, and 5 is in the list at index 4. So let's see if that's correct. 0, 1, 2, 3, 4. And of course, because the shuffling is random, we should get it in different places. So here 5 is in the list, and 5 is in the list at index 0. So that looks like it's working correctly. Now, the next thing we want to think about is sorting. So sorting is a very interesting topic in computer science, and we're going to study it in a few weeks. Let's think about how we would sort 3, 1, 4, 2, 5. You can undoubtedly do this in your head very fast, And you can see that it's 1, 2, 3, 4, 5, just like that. But we need to think a little bit more strategically about it and a little more slowly about how this is actually going to work. So how do we know that one comes first? Well, one way to think about it is we step through all of these elements and pick out the one that's the smallest. So how are we going to figure out which one is the smallest? What method do we have to use? Now, this can't use the equals method because equals will just tell us if it's the same or not. We need more information. We need to know whether the value is bigger or smaller. So with primitive data, we would use less than, but less than isn't available for objects, at least not in Java. So objects use methods, not operators, so we need to find a meaningful method in the string class. So let's go to the string class. Okay, so here are our string class methods. Now what we see is we have methods like compare to, and it says it compares two strings lexicographically. Ooh, big word. Then we have compare to ignore case. That could be interesting too. Let's read a little bit more about these methods. Compares two strings lexicographically. The comparison is based on the Unicode value of each character in the strings. The character sequence represented by the string object is compared lexicographically to the character sequence represented by the argument. The result is negative if this string object precedes the argument string. The result is positive if this string object follows the argument string, and the result is 0 if the strings are equal. So compare to returns 0 exactly when equals method would return true. Here's the definition of lexicographic ordering. If two strings are different, then they either have different characters at the same index, that's a valid index for both strings, or their lengths are different or both. If they have different characters at more than one position, let k be the smallest index. Okay, so what are they trying to describe here? Well, what they're saying is they start at the left and step through the characters one at a time. If the characters are not the same, the one that's the smaller character, and this is an ASCII character, that's the one that's going to be the smaller string. Now, if they get to the end of one of the strings, that string is the smaller string. And if they get to the end of both strings at the same time with all the characters being equal, well, that's the equals case. So, a lot of words, but in this case, the description here is actually completely useful and correct and makes sense. The API isn't always like that, as you know. Is compared to an instance method or a class method. You could get that from the API by looking to see whether it has static in front of it. But you also could think about it. When we were reading through that description, it talked about this object. And remember, it had only one parameter. So this has to be an instance method because the other string is going to have to be passed in as an object. Now, if that reasoning doesn't make sense just yet, keep thinking about it. Eventually it will. So it's going to return a negative number, 0, or a positive number. And those mean whether the strings are less than, 0, or positive. It's available in the string class, and it's available in many, many other classes where order makes sense. So for example, double, integer, character, and Boolean, all of these classes have a compare to method. Let's think about things like point, or paper, or rectangle 2D. Does it make sense for the point class to have comparisons? What would it mean for a point to be less than another point? I can't think of anything that makes sense. So let's go and take a look in the API. Here's our point class. And when we look at our methods, which is a mercifully short number of methods, you'll notice there is no compare to method. So in this particular case, you can't make a comparison with points. That means we couldn't sort an array of points. And that's fine because it doesn't make sense to sort an array of points. The same thing is true about paper and rectangle 2D.double. Sorting doesn't make sense here. Comparison doesn't make sense. And so since those don't make sense, there is no compare to operation. So let's sort the array list we previously shuffled. I want to comment out our previous experiment. Go to experiment 4. Our setup will be the same, so we'll just copy that in. And here's how we sort. Collections.sort my list and system out print line my list. Well, very nicely sorted, worked very easily. So notice sorting in the collections class is a one-line command. Very handy thing, although someday we may get curious and try to figure out what's going on inside that command. Now, what happens if we try to sort an array of point objects? This is always a good thing to know, is what happens if you do something that you don't expect is really going to work. Well, first let's comment out experiment 4 and go to experiment 5. Now the setup's going to be kind of similar. We're going to have to change it a little bit. Okay, so instead of an array list of integer, we're going to have an array list of points. And instead of adding an integer, we're going to add a point. Now, you may not remember the point constructor, but it takes 2 parameters, because like an x and y coordinate. Then we shuffle, then we sort. Oh, wait a minute, what happened here? Notice that Eclipse is not happy. So let's take a look and see what the error message is. Bound mismatch. The generic method sort of type collections is not applicable for the argument array list of point. The inferred type point is not a valid substitute for the bounded parameter t extends comparable !, super t, angle bar. Ooh, that's ugly. So what we got was a crazy, ugly, unhelpful error message. But we were expecting an error to occur. We really didn't think this was going to work because it doesn't make sense to sort points. So while Java is not giving us anything very useful here, it is telling us that this is not going to work and we're not going to be able to do it. Now, the next thing we should do is reconsider searching. The search method in collections is called binary search, and this is really a cool trick. We're also going to look at the details of this later, but for now, let's just give you a little big picture understanding of what's going on. Here's the general idea. Look up things like you would in a phone book. When you pick up a phone book to look up a friend's address, of course, I realize probably you guys do a search on the internet now instead of picking up a phone book, but play along with me. I know you've all seen a phone book. You don't start at the first page and read the first name and then the second name and the third name. That would be crazy. The names are in order. So what you do is you sort of jump to the part of the book where you think the name might be, and then see if it's bigger or smaller. If it's bigger, you go to the later half of the book, and if it's smaller, you go to the earlier half of the book. And then you repeat that process. So you start at the middle, which basically gets rid of half of the remaining possibilities at each step. It's really cool. It is crazy fast. But the thing is, it only works on sorted data. So if your data isn't sorted, binary search is impossible. Now, the collections class does not check that your data is sorted. So this is something you have to remember when you're using binary search. And of course, this is going to use comparison, because notice we were saying if the data is bigger or smaller. Well, bigger or smaller, that means less than or greater than, and compare to is the method that fills in for those. So here's example 6. Let's use binary search to find out if 5 is in our array list. Now remember, we know this didn't work, so we're going to have to comment it out. So I'm going to go back to experiment 4. Of course, commenting out experiment 5 to grab our setup. So first we call shuffle, then we call sort, and now we're going to do our search. Well, you know, we did some work on that earlier too. So let's grab that. Whoops, that's not the right part. We wanted to just create the integer value 5. You know, that probably would have been quicker to type than to try to copy, but hey. So now we're going to do collections.binary search for value. So let's see what Eclipse isn't happy about. Oh, I see what the problem is. I forgot to give it the list. My list for value. There we go. Without the list, it doesn't really stand a chance. Now, we haven't talked about what binary search returns. So we may get a little surprise here, but surprises are okay. So we have our shuffle data, then we sort it, and we were looking for 5 and it returns 4. 0, 1, 2, 3, 4. Looking good. Now, what would happen if we try something that isn't in there? So let's do a search for -3. It returns a -1. So it gives us a hint that it's not in there, a negative index being a good hint. So that makes sense. Now, let's see what happens if we don't sort. Okay, so what it says is it didn't find 5. Now, it's particularly poignant in this case because 5 is in the first position. But notice that it just went ahead and ran the binary search where it was starting at the middle and trying to find the spot based on that. And because the 10 was in the middle, it got redirected to the wrong side. And once it's redirected, it can't find its way around. The other thing to notice is the method didn't fail and the compilation didn't fail. So this is a very important responsibility of the programmer, is to make sure that things are sorted before you try to do binary search. We found the smallest and biggest elements amongst primitive data, and we used less than. And that suggests that compare to is something that's going to be necessary here too. So let's find the smallest and largest elements in our array list. You see we're on our last experiment here. So let's grab our setup again. In this case, I don't think we want to sort things. So system out print line. The minimum is plus collections.min of my list. And system out print line, the maximum is plus collections.max of my list. So here we go. Now we expect that minimum is going to be 1 and the maximum is going to be 10 because that's what we put into the list. Minimum is 1, maximum is 10. Things are looking good. Let's look at the big picture of what we've done. We've used experimentation to explore a useful and interesting part of the Java API. Now, it was a little scary, particularly reading the collection stuff is scary. We've used it in situations where we know the answers to assure that things are working the way that we expect. And in fact, this kind of experimentation is what I typically do when I find a new class that I think I want to use for something. I do it in a separate program. I don't document the program carefully or even really design it carefully. I just learn what the ins and outs of the class are. It's really a lot of fun. So keep programming.